vast darkness of space surrounds us, punctuated by billions of gleaming stars. In this cosmic ocean, we are but a single droplet, adrift on currents we're only beginning to understand. Gentle music plays as the screen fades in from black. A soft narrator's voice begins, a slow pan across the Milky Way. Narration: out there, beyond the shimmer of stars and galaxies we can see, lies a vast, unseen world, a realm that silently governs the universe yet remains cloaked in darkness. Tonight, we drift into that mysterious space, the invisible universe. As we look up at the night sky, we see only a fraction of what exists. The stars that twinkle overhead, the planets that wander among them, even the distant galaxies that spiral through the void. All of these are merely the visible manifestation of a much deeper reality. The universe keeps its greatest secrets hidden from our eyes. Forces that have no form shape galaxies into cosmic webs. Energy with no source pushes the boundaries of creation ever outward. And matter that casts no shadow makes up the majority of all that exists. Tonight, we journey into this shadow realm. We'll explore the mysteries that lie beyond human vision, beyond even the most powerful telescopes. We'll venture into a universe where light itself becomes trapped, where time stretches and bends, and where the very foundations of reality reveal themselves to be stranger than we ever imagined. This is not a journey of fear, but of wonder. As you listen, let your mind drift through these cosmic mysteries. Let the gentle currents of gravitational waves rock you. Let the dark matter cradle you in its invisible embrace. Let the vastness of space become a comfort rather than a terror. For in understanding the invisible universe, we understand ourselves better. We are made of the same star stuff that fills the cosmos. The same forces that shape galaxies once shaped our bodies. The same mysterious dark energy that expands the universe flows through the empty spaces between our atoms. So close your eyes, breathe deeply, and join me as we drift into the shadows between the stars, where the universe's greatest mysteries await. The journey begins now as we first explore what we can see, before venturing into what remains hidden. The visible universe is beautiful and vast, but it is merely the surface of a much deeper ocean of existence. Let us dive beneath that surface together. Before we venture into the darkness, let us first bask in the light. Our visible universe is a symphony of radiance, a dance of photons that has been ongoing for 13.8 billion years. When we gaze at the night sky, we see stars as they were, not as they are. Light from Proxima Centauri, our nearest stellar neighbor, takes 4.2 years to reach us. The light from Andromeda Galaxy has traveled 2.5 million years across the void to grace our eyes tonight. We are always looking into the past, watching a cosmic history unfold before us. This celestial light show begins with stars, massive furnaces of nuclear fusion. Our own star, the Sun, transforms 400 million tons of hydrogen into helium every second. This atomic alchemy releases energy in the form of photons that bathe our world in warmth and light. Across the universe, stars of different sizes and temperatures paint the cosmos in a palette of colors, from the cool reds of aging red giants to the hot blues of massive young stars. The life cycle of a star tells us much about the visible universe. Born in clouds of gas and dust, stars begin as protostars, dense knots of matter that grow hotter as gravity compresses their cores. When temperatures reach millions of degrees, nuclear fusion ignites and a new star is born. For most of its life, a star maintains a delicate balance between the outward pressure of its nuclear furnace and the inward pull of gravity. Our Sun is currently in this stable middle age where it will remain for another 5 billion years. When stars exhaust their nuclear fuel, their fate depends on their mass. Smaller stars like our Sun will expand into red giants before shedding their outer layers as planetary nebulae, cosmic clouds of glowing gas that spread their star-forged elements into space. The core remains as a white dwarf, a dense, cooling ember that will slowly fade over trillions of years. More massive stars face a violent end as supernovae, cosmic explosions so bright they can outshine. In these cataclysmic events, heavier elements are forged in seconds and scattered across space. What remains might be a neutron star, a city-sized sphere so dense that a teaspoon of its matter would weigh billions of tons on Earth, or for the most massive stars, a black hole, where gravity becomes so intense that nothing, not even light, can escape. Stars cluster together into galaxies, vast cosmic neighborhoods, and trillions of stellar residents. Our Milky Way galaxy is a barred spiral, with elegant arms sweeping outward from a central bulge. Within these arms, nebulae, clouds of gas and dust, glow with the reflection or shine with their own luminescence as stellar nurseries where new stars are born. Galaxies themselves form even larger structures. They gather in clusters bound by gravity, and these clusters arrange themselves in vast cosmic webs along invisible filaments. Between these structures lie enormous voids, spaces stretching millions of light years containing almost nothing at all. This large-scale structure of the universe resembles a cosmic sponge or a network of soap bubbles, with galaxies outlining the edges of mostly empty regions. These visible wonders reveal themselves to us across the electromagnetic spectrum. While our eyes can only perceive visible light, the universe broadcasts on many channels. Radio waves from distant quasars, infrared heat from cosmic dust, ultraviolet radiation from hot stars, X-rays from neutron stars, and gamma rays from violent cosmic explosions, all are forms of electromagnetic radiation, different only in their wavelengths and energies. Our modern telescopes act as cosmic translators, converting these invisible signals into images we can comprehend. The Hubble Space Telescope has revealed galaxies colliding in silent, slow-motion impacts that unfold over millions of years. Radio telescopes have mapped the hydrogen gas that fills the space between stars. Infrared observatories peer through cosmic dust to reveal stars in the process of formation. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, bathes all of space in a nearly uniform warmth of about 3 degrees above absolute zero. This ancient light has been traveling for over 13 billion years, carrying with it the earliest information about our universe's infancy. The slight temperature variations in this background radiation, differences of mere millionths of a degree, reveal the seeds from which all structure in our universe grew. These tiny fluctuations, imprinted when the universe was just 380,000 years old, represent the earliest blueprint of today's cosmic architecture of galaxies and voids. Interstellar dust forms complex molecules in the cold reaches between stars. Some of these molecules are organic compounds, carbon-based chemicals that form the building blocks of life. The ingredients for life as we know it were cooked in stellar furnaces and scattered across space by supernovae explosions, only to be gathered again by forming planets. Planets, moons, asteroids, and comets represent matter condensed into larger bodies. Our solar system formed from a spinning disk of dust and gas around our young sun. The rocky inner planets gathered heavy elements, while the outer gas giants captured lighter hydrogen and helium. This pattern of world building likely repeats around countless stars throughout the cosmos. We now know that most stars host planetary systems of their own. Exoplanets, worlds orbiting other stars, come in a stunning variety. Hot Jupiters orbit perilously close to their stars. Super-Earths exist in a size class absent from our solar system, and potentially habitable worlds, similar in size to our Earth and orbiting within their star's Goldilocks zone, might harbor conditions suitable for life as we know it. Comets and asteroids, the solar system's smaller denizens, are cosmic time capsules. These relatively unchanged remnants from our solar system's formation carry chemicals and water that may have seeded Earth with the ingredients for life. When they impact planets, they can bring both destruction and the raw materials for new beginnings. All of these visible wonders, from the smallest dust particles to the largest galaxy clusters, are made of ordinary matter. Scientists call this baryonic matter, the protons, neutrons, and electrons that make up atoms. This is the stuff that emits, absorbs, and reflects light. It's the matter we can touch, see, and directly measure. Yet for all its splendor, for all its vastness, this visible universe accounts for a mere 5% of all that exists. 95% of our cosmos is invisible to our eyes and instruments. It neither emits nor absorbs light. It reveals itself only through its gravitational effects on the visible universe. As we drift among the stars, marveling at their brilliance, let us remember that we are seeing only the surface of a much deeper reality. Like swimmers floating on the ocean's surface, unaware of the vast depths below, we have been skimming along the visible surface of the cosmos. Now, it's time to dive deeper. But even with all this beauty, all this light, we're only seeing a fraction. In the spiral arms of galaxies, Stars orbit around a central point like cosmic carousels. According to the laws of physics that govern our everyday world, stars on the outskirts of these galaxies should move more slowly than those near the center, just as the outer planets in our solar system orbit the Sun more slowly than Mercury or Venus. Yet when astronomers measured the rotation of galaxies, they discovered something peculiar. Stars at the edges were moving much faster than expected. This discovery was first made in the 1930s by Swiss astronomer Fritz Zwicky, who studied the Coma galaxy cluster. He calculated that the visible matter in this cluster could not possibly generate enough gravity to hold it together. The galaxies were moving so quickly that they should have escaped each other's gravitational pull long ago, yet they remained bound together as a cluster. Zwicky proposed that some invisible dark matter must be providing the extra gravitational glue. For decades, few took Zwicky's ideas seriously. Then, in the 1970s, American astronomer Vera Rubin meticulously measured the rotation curves of numerous galaxies. Her observations confirmed what Zwicky had suspected. Galaxies were rotating too quickly at their edges. Something invisible was influencing their motion. The evidence for dark matter could no longer be ignored. Imagine a spinning ice skater. When she extends her arms, she slows down. When she pulls them close, she speeds up. This is the conservation of angular momentum. Similarly, stars at the edges of galaxies should slow down compared to those near the center, but they don't. It's as if each galaxy is embedded in a large, invisible cloud of matter that extends far beyond the visible disk. These dark matter halos cannot be seen directly. They emit no light, no radio waves, no radiation of any kind that we can detect. Yet their gravitational influence shapes everything we can see. They are cosmic puppeteers, invisible hands guiding the dance of stars and galaxies. Perhaps the most compelling evidence for dark matter comes from an object called the Bullet Cluster. This cosmic collision between two galaxy clusters allows us to observe something remarkable. The visible matter, primarily in the form of hot gas, slowed down during the collision, while the dark matter halos of the two clusters passed right through each other, unaffected. Gravitational lensing, the bending of light from distant galaxies, reveals that most of the mass in this system is not where the visible matter is. This separation between visible and invisible mass can only be explained if dark matter is real. But what exactly is this mysterious substance? Whatever it is, it must be fundamentally different from the ordinary matter that makes up stars, planets, and people. It cannot interact with light or other forms of electromagnetic radiation. It passes through normal matter as if it weren't there, yet it exerts gravitational pull on everything around it. Scientists have proposed various candidates for dark matter particles. The leading contenders are WIMPs, weakly interacting massive particles. As their name suggests, these particles would interact weakly with ordinary matter, making them difficult to detect, yet they would have enough mass to account for dark matter's gravitational effects. Axions represent another possibility. These hypothetical particles would be much lighter than WIMPs, but could exist in such enormous numbers that they would collectively contribute substantial mass to the universe. Unlike WIMPs, which would be heavy relics from the early universe, axions might still be produced today in extreme environments like the cores of stars. Sterile neutrinos offer a third option. Regular neutrinos, ghostly particles produced in nuclear reactions, barely interact with normal matter. Trillions pass through your body every second without effect. Sterile neutrinos would be even more aloof, interacting only through gravity. If they exist, they could account for some or all of dark matter. Deep underground, in laboratories shielded from cosmic radiation, scientists have built elaborate detectors to hunt for these elusive particles. Some use tanks of liquid xenon, cooled to nearly absolute zero. Others employ crystals of germanium or silicon. All wait patiently for the rare moment when a dark matter particle might bump into an atom of ordinary matter, producing a tiny flash of light or a minute release of heat. So far, these detectors have found nothing conclusive. Dark matter continues to elude direct detection, remaining known only by its gravitational effects. This has led some scientists to propose alternative explanations. Perhaps our understanding of gravity itself needs revision. Theories like modified Newtonian dynamics, or MOND, suggest that gravity might behave differently at the vast scales of galaxies than it does in our solar system. Yet most evidence still points to dark matter as the most likely explanation. Computer simulations of cosmic evolution show that without dark matter, the universe as we know it could not have formed. The delicate filaments of the cosmic web, the hierarchy of galaxy clusters and superclusters, all require dark matter's invisible scaffolding to take shape. The distribution of dark matter throughout the cosmos tells a story of structure formation. In the early universe, dark matter began clumping together under its own gravity, forming wells of gravitational attraction. Ordinary matter was drawn into these wells, eventually becoming dense enough to form stars and galaxies. This process explains why galaxies are not randomly distributed, but form patterns across the cosmos. They follow the underlying dark matter framework. If we could see dark matter, the night sky would look dramatically different. Instead of isolated points of starlight, we would see vast, diffuse halos enveloping each galaxy, extending far beyond their visible edges. These halos would connect to each other in a cosmic web, with galaxies situated at the nodes where filaments intersect. The apparent emptiness between galaxies would reveal itself as being filled with tenuous bridges of dark matter. Perhaps most intriguingly, dark matter might not be completely dark after all. Some theories suggest that dark matter particles might occasionally annihilate each other when they collide, producing brief flashes of gamma rays. Others propose that dark matter particles might slowly decay over cosmic timescales, releasing detectable radiation. Astronomers search for these subtle signals from the cores of galaxies or from dwarf satellite galaxies, where dark matter is thought to be most concentrated. The quest to understand dark matter connects the largest scales of the universe to the smallest. It links cosmology, the study of the universe as a whole, with particle physics, the study of nature's most fundamental building blocks. This invisible substance may hold the key to unifying our understanding of the cosmos across all scales. As our instruments become more sensitive and our models more sophisticated, we edge closer to unveiling this cosmic mystery. The discovery of dark matter's true nature would represent one of the greatest breakthroughs in the history of science, comparable to the discoveries of general relativity or quantum mechanics. For now, dark matter remains a shadow player on the cosmic stage, unseen but undeniably present. Its gravitational fingerprints are everywhere, shaping the visible universe we observe. If dark matter is the invisible hand shaping cosmic structures, dark energy is the gentle breath pushing them apart. While one builds, the other dissolves. While one binds, the other liberates. Together, they form a cosmic duet that governs the fate of our universe. The story of dark energy begins with Albert Einstein. In 1915, when formulating his theory of general relativity, Einstein believed the universe was static, neither expanding nor contracting, but his equations suggested otherwise. They predicted a universe that would collapse under its own gravity. To counteract this, Einstein introduced a cosmological constant, a repulsive force that would balance gravity's pull and keep the universe stable. The universe wasn't static after all. It was growing larger with time. Galaxies were moving away from each other, carried along by the expansion of space itself. For decades, astronomers assumed this expansion would gradually slow down, as gravity pulled galaxies back toward each other. The big question seemed to be whether the universe contained enough matter to eventually halt the expansion and reverse it into a big crunch, or whether it would expand forever, albeit at an ever-decreasing rate. Then came one of the most startling discoveries in modern cosmology. In the late 1990s, two independent teams of astronomers set out to measure the deceleration of the universe's expansion. Using type Ia supernovae as standard candles, cosmic explosions whose intrinsic brightness is known, they could calculate how fast the universe was expanding at different times in its history. The results were astonishing. The universe wasn't slowing down at all. It was speeding up. The expansion of space was accelerating. This finding contradicted everything scientists thought they knew. What force could possibly be powerful enough to overcome gravity's pull and push galaxies apart at an ever-increasing rate? The discovery was so unexpected, so paradigm-shifting, that the leaders of the two research teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. They had uncovered a fundamental aspect of our universe that had remained hidden until then. Dark energy, it turns out, comprises roughly 68% of everything in the cosmos. Combined with dark matter at 27%, this means that 95% of our universe consists of things we cannot directly observe. The stars, planets, galaxies, and all other visible matter make up a mere 5% of reality. We are, in a very real sense, living in a shadow universe, seeing only the faintest outlines of what truly exists. But what exactly is dark energy? Scientists have proposed several possibilities. Perhaps the most straightforward explanation is that Einstein's cosmological constant has returned from scientific exile. Maybe empty space itself possesses an intrinsic energy, a vacuum energy that pushes outward as the universe expands. This would align with quantum physics, which suggests that even perfect vacuums fluctuate with energy. Another possibility is quintessence, a dynamic field that varies across time and space. Unlike the cosmological constant, which would remain unchanging, quintessence could strengthen or weaken over cosmic history. Some models suggest it might eventually fade away, allowing gravity to reclaim dominance. A third, more radical idea is that our understanding of gravity needs revision. Perhaps general relativity, while extraordinarily accurate at solar system scales, breaks down over the vast distances of intergalactic space. Modified gravity theories attempt to explain both dark matter and dark energy as misinterpretations of how gravity behaves at different scales. Whatever its nature, dark energy profoundly shapes our cosmic destiny. If it remains constant or increases with time, the universe will expand forever. Galaxies outside our local group will recede beyond our visual horizon. In the far future, trillions upon trillions of years from now, observers would see only a handful of nearby galaxies, all others having disappeared beyond the cosmic horizon, their light too redshifted to detect. Dark energy also influences our understanding of cosmic history. When the universe was young and matter was densely packed, gravity dominated over dark energy's subtle push. This allowed galaxies and galaxy clusters to form. But as space expanded and matter spread out, dark energy's influence grew relatively stronger. About 5 billion years ago, it overtook gravity as the dominant force shaping cosmic evolution. We live in an epoch where dark energy has just recently claimed the cosmic throne. The accelerating expansion raises profound philosophical questions. If the universe continues to expand forever, eventually all stars will burn out. Black holes will evaporate through Hawking radiation. Even protons might decay. The cosmos could face a heat death, a state of perfect equilibrium where nothing happens because nothing can happen. Entropy, a measure of disorder, would reach its maximum. Time, in any meaningful sense, would cease, or perhaps dark energy will increase until it overcomes not just gravity, but the electromagnetic, weak and strong nuclear forces as well. Either way, dark energy confronts us with the impermanence of everything we see. The stars that seem eternal are merely temporary lanterns in an ever-darkening cosmos. The galaxies that appear immutable are slowly being pulled apart. Even the laws of physics that feel so solid might be mere quirks of our particular cosmic era. Yet within this seeming pessimism lies a profound wonder. We exist in the sweet spot of cosmic history, a time when stars still shine, when galaxies are still visible, when complexity can still arise. We live in an epoch where the universe is comprehensible. Earlier, it was too dense and hot for structures like us to exist. Later, it may be too diffuse and cold. Dark energy also connects to the question of our universe's birth. The leading theory of cosmic inflation suggests that the very early universe underwent a period of exponential expansion, driven by a force that behaves remarkably like dark energy. Perhaps dark energy is inflation's distant echo, a reminder of our universe's explosive origins. Meanwhile, efforts to detect and characterize dark energy continue. Space-based observatories like the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will map billions of galaxies to track how cosmic structures evolved under dark energy's influence. Ground-based projects like the Dark Energy Spectroscopic Instrument create three-dimensional maps of the universe, revealing how dark energy has shaped cosmic geography. For now, dark energy remains the dominant mystery of modern cosmology, a force we can measure but cannot see, whose effects we can track, but whose nature eludes us. It is the silent breath of the cosmos, gently but inexorably pushing the universe toward its ultimate fate. If dark matter holds things together, dark energy pushes them apart. Two forces in balance, one creating structure. At the edge of physics, where mathematics stretches toward infinity and light itself surrenders to darkness, we find black holes, cosmic objects so extreme they blur the line between the possible and impossible. Neither truly holes nor completely black, these gravitational monsters represent nature at its most fundamentally strange. A black hole begins with a star's death. When a massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel, the outward pressure that kept it stable against its own gravity suddenly vanishes. The star's core collapses inward with devastating speed. The outer layers rebound off this collapsing core in a supernova explosion that can briefly outshine an entire galaxy. What remains at the center depends on the star's initial mass. For the most massive stars, the collapse continues relentlessly. As gravity crushes the core into an ever smaller volume, the density and gravitational pull increase beyond comprehension. Soon, the mass becomes so concentrated that nothing, not even light traveling at 186,000 miles per second, can escape. A black hole is born. The boundary marking this point of no return is called the event horizon. It's not a physical surface, but rather a mathematical boundary in space-time. Cross this invisible border, and you can never return to the universe you knew. All paths forward in time lead inexorably toward the center of the black hole. What lies beyond the event horizon remains one of science's greatest mysteries. Einstein's general relativity, our best theory of gravity, predicts that all the matter falls toward a point of infinite density called a singularity. Here, the known laws of physics break down entirely. Space and time become so distorted that conventional concepts lose meaning. Scientists suspect that quantum mechanics must somehow merge with general relativity to resolve these infinities. But a complete theory of quantum gravity remains elusive. Around a black hole, space itself flows like a river toward a waterfall. This creates a region outside the event horizon where space is dramatically warped. Light that passes through this region doesn't travel in straight lines, but follows curved paths dictated by the black hole's gravitational field. This phenomenon allows black holes to act as cosmic lenses, bending and magnifying light from distant objects behind them. If you were to watch a friend fall into a black hole, you would witness something remarkable. As they approach the event horizon, time itself would appear to slow down from your perspective. Their movements would become increasingly sluggish, and the light from them would shift toward the red end of the spectrum. Eventually, they would seem frozen at the event horizon, their image growing dimmer and redder until it faded from view. From your friend's perspective, however, nothing unusual would happen at the event horizon itself. Black holes come in different sizes. Stellar mass black holes formed from collapsed stars typically have masses between 5 and several dozen times that of our Sun, compressed into a region smaller than a city. Intermediate mass black holes remain somewhat mysterious, but may fill the gap between stellar and supermassive varieties. Supermassive black holes lurk at the centers of most large galaxies, including our own Milky Way. Our galactic center hosts Sagittarius A star, pronounced Sagittarius A star, a black hole with a mass of about 4 million suns. Despite this enormous mass, it would fit comfortably within the orbit of Mercury. The largest known supermassive black holes can reach tens of billions of solar masses. How these cosmic leviathans grew so large remains an open question. Did they form from the collapse of enormous clouds of gas in the early universe? Did smaller black holes merge to create larger ones? Or perhaps they grew steadily by consuming surrounding matter over billions of years? The answer likely involves a combination of these processes. In 2019, humanity captured the first direct image of a black hole, or more precisely, the hot gas orbiting its event horizon, using the Event Horizon Telescope. This global network of radio telescopes functioned as a virtual observatory the size of Earth, allowing unprecedented resolution. The subject was the supermassive black hole at the center of galaxy Messier 87, located 53 million light-years away. The image revealed a glowing asymmetric ring surrounding a dark center, the shadow of the black hole itself. What happens to information that falls into a black hole has troubled physicists for decades. Quantum mechanics suggests that information cannot be destroyed, yet anything that crosses the event horizon seems lost forever. This information paradox has led to exotic proposals like black hole firewalls at the event horizon, or the idea that black holes store information in two-dimensional patterns on their event horizons, like cosmic holograms. Stephen Hawking's groundbreaking work in the 1970s revealed that black holes aren't entirely black. Quantum effects near the event horizon cause them to emit a faint radiation, now called Hawking radiation. Over enormously long timescales, far longer than the current age of the universe for stellar mass black holes, this radiation would cause black holes to evaporate completely, returning their mass to the universe as energy. When black holes orbit each other in binary systems, they create ripples in space-time called gravitational waves. As they spiral closer together, these waves intensify until the black holes merge in a final cosmic collision. Such mergers release more energy than all the stars in the observable universe combined. Yet this energy emerges not as light, but as gravitational waves that subtly stretch and compress space itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected these waves for the first time, confirming a major prediction of Einstein's general relativity and opening a new window on the universe. The signal came from two black holes, about 29 and 36 times the mass of our Sun, spiraling together and merging 1.3 billion light-years away. Black holes don't just destroy, they also create. The intense radiation from matter falling into supermassive black holes can trigger star formation in surrounding gas clouds. When especially large amounts of matter fall in, the black hole becomes an active galactic nucleus, shooting enormous jets of particles and energy thousands of light-years into space. These jets can influence the evolution of entire galaxies. In some ways, black holes are the simplest objects in the universe. According to the no-hair theorem, a black hole can be completely described by just three parameters: mass, electric charge, and angular momentum, or spin. All other information about what formed the black hole, whether it was stars, planets, or exotic matter, is lost. Yet this simplicity masks profound complexity. Black holes exist at the intersection of our two most successful but incompatible physical theories, general relativity and quantum mechanics. Understanding them fully may require a revolution in physics, as significant as either of those theories. The seemingly monstrous nature of black holes has inspired both fear and fascination in popular culture. They've been portrayed as cosmic destroyers, interstellar shortcuts, and even gateways to other dimensions. The scientific reality is no less wondrous. These cosmic objects represent the most extreme environments in our universe, places where density, gravity, and the curvature of space-time reach their ultimate limits. If you could somehow hover safely near a black hole's event horizon, you would witness extraordinary phenomena. Matter spiraling inward would form a superheated accretion disk glowing across the electromagnetic spectrum. Magnetic fields would channel some of this material into jets perpendicular to the disk. And if you looked at the seemingly empty space behind the black hole, you might see multiple images of the same distant stars, light that has been bent around the black hole's intense gravitational field. Scientists have even heard black holes through the gravitational waves they generate. When converted to sound waves within human hearing range, a black hole merger creates a distinctive chirp, rising in pitch and volume before suddenly stopping as the black holes combine. This cosmic percussion provides yet another way to study these mysterious objects. For all their cosmic drama, black holes follow the same physical laws that govern less extreme objects. They are not supernatural anomalies but natural consequences of gravity's unbounded strength. They remind us that our universe contains wonders strange enough to surpass even our most creative imaginings. From the vantage point of Earth, stars appear as isolated points of light scattered across the night sky. Galaxies seem like distant islands, separated by vast oceans of emptiness. But this perception is an illusion born of our limited perspective. When we step back and observe the universe on its larger scales, a different pattern emerges, one of connection rather than isolation, of structure rather than randomness. The cosmos forms an intricate tapestry astronomers call the cosmic web, a vast network of filaments, sheets, and nodes stretching across billions of light years. This grand architecture represents the largest known structure in the universe, a pattern so vast that entire galaxy clusters appear as mere dewdrops along its silken strands. The story of the cosmic web begins in the earliest moments after the Big Bang. Quantum fluctuations, tiny variations in density caused by the uncertainty principle of quantum mechanics, were stretched to cosmic scales during the inflationary period of the universe's first fraction of a second. These microscopic differences in density became the seeds from which all cosmic structure would grow. As the universe expanded and cooled, regions with slightly higher density exerted slightly stronger gravitational pulls on their surroundings. Dark matter, responding only to gravity and unimpeded by radiation pressure, began clumping together first. Ordinary matter eventually followed, flowing into these gravitational wells. This process of gravitational attraction amplified the initial tiny variations into the vast cosmic structures we observe today. Computer simulations reveal how this process unfolded. When scientists model the evolution of a universe containing dark matter, ordinary matter, and dark energy, starting with conditions matching those observed in the cosmic microwave background radiation, a familiar pattern emerges. Matter doesn't distribute itself uniformly, nor does it form isolated spherical clusters. Instead, it creates an intricate web-like structure, eerily similar to biological systems like neurons or fungal networks. This cosmic web consists of several distinct components. At the densest intersections of filaments lie galaxy clusters, the cosmic web's nodes. These gravitational powerhouses contain hundreds or thousands of galaxies, vast reservoirs of superheated gas, and enormous concentrations of dark matter. The most massive clusters, like the Coma cluster or the Bullet cluster, can contain the mass equivalent of quadrillions of suns. Connecting these clusters are the cosmic web's filaments, elongated bridges of matter that can span hundreds of millions of light years. These cosmic highways channel gas toward the clusters and provide pathways along which galaxies move. Many galaxies, including our own Milky Way, reside within these filaments, like houses along a country road. Where multiple filaments flatten and merge, they create two-dimensional structures called sheets or walls. The most famous of these is the Great Wall, a sheet of galaxies stretching more than 500 million light-years across. From within such structures, galaxies appear to surround us in a flattened distribution, like towns built on a vast plain. Between the filaments, sheets, and clusters lie cosmic voids, enormous bubbles of near emptiness that can span hundreds of millions of light-years. These voids aren't completely empty. They contain a sparse population of galaxies and diffuse gas, but their density is far below the cosmic average. Nearly 60% of the volume of the universe consists of these voids, making emptiness the predominant state of the cosmos. This web-like structure represents a fundamental organizing principle of the universe. It's not a random pattern, but a direct consequence of how gravity shapes matter across cosmic scales. Dark matter forms the scaffolding of this web, with ordinary matter, the stuff of stars and planets, tracing its outline like luminous paint highlighting an invisible frame. We can observe this cosmic web through various means. Galaxy surveys map the positions of millions of galaxies, revealing their tendency to cluster along unseen filaments rather than distribute randomly. X-ray observations detect the superheated gas within galaxy clusters and along some of the denser filaments. And gravitational lensing, the bending of light by gravity, allows us to map dark matter concentrations, revealing the invisible skeleton of the cosmic web. More recently, astronomers have detected the cosmic web background, faint, diffuse light emitted by intergalactic gas illuminated by nearby galaxies. This tenuous glow traces filaments too sparse to contain many galaxies, but still rich in diffuse hydrogen gas. Through specialized techniques like integral field spectroscopy, scientists can now directly observe the cosmic web's gaseous component, confirming theoretical predictions about its structure. The cosmic web isn't static, it evolves over billions of years. In the early universe, the web was more uniform, with smaller, more numerous filaments and less pronounced voids. As time passed and the universe expanded, gravity enhanced the contrasts. Matter flowed out of voids and along filaments toward clusters, making the dense regions denser and the empty regions emptier. Dark energy's accelerating expansion now stretches the cosmic web, gradually severing connections between distant parts of the universe. Within this grand cosmic framework, galaxies follow prescribed paths. They tend to move along filaments toward clusters, like water flowing through a watershed toward a lake. As they travel, they interact with their environment and with each other. Gas flows into galaxies from the surrounding filaments, fueling new star formation. Meanwhile, galaxies in denser regions often collide and merge, forming larger composite galaxies with complex structures. A galaxy's properties correlate strongly with its position in the cosmic web. Massive elliptical galaxies tend to reside in clusters, where frequent interactions with other galaxies have stripped away their gas and disrupted their orderly rotation. Spiral galaxies like our Milky Way are more commonly found in filaments, where they can maintain their delicate disk structures and continue forming new stars. And in the emptiest voids, we find small, gas-rich dwarf galaxies that have evolved in relative isolation. Our own local cosmic neighborhood reflects this larger pattern. The Milky Way belongs to the local group, a small galaxy cluster that includes Andromeda and about 50 smaller galaxies. This group, in turn, sits near the outskirts of the Virgo supercluster, a collection of galaxy groups and clusters. And the Virgo supercluster forms part of an even larger structure called Laniakea, a complex network of filaments and clusters spanning more than 500 million light-years. Beyond our local neighborhood, astronomers have identified even larger structures, massive walls of galaxies like the Sloan Great Wall, enormous voids like the Bootes Void, and the mysterious cold spot in the cosmic microwave background that might indicate a supervoid billions of light-years across. These structures push toward the theoretical limit of how large cosmic features can grow, given the universe's age and expansion rate. The cosmic web also serves as an enormous reservoir of gas, the raw material for future star formation. Much of the universe's ordinary matter resides not in galaxies, but in the warm, hot intergalactic medium, WIM, threading through the cosmic web's filaments. This diffuse gas, heated to millions of degrees by shockwaves from cosmic expansion and galactic outflows, contains most of the universe's oxygen, carbon, and other heavy elements produced in stars and scattered through space by supernova. As galaxies move through this medium, they both gather material from it and contribute to it. Gas falls into galaxies, fueling star formation, while energetic processes like supernovae and active galactic nuclei blast gas back into intergalactic space, enriching the cosmic web with heavy elements. This cosmic recycling system creates a continuous exchange between galaxies and their environment. For all its vastness, the cosmic web represents a profound form of connection. No galaxy is truly isolated. Each is embedded within this larger structure, influenced by distant masses through gravity's invisible threads. Even the seemingly empty voids play a crucial role, their negative pressure helping to channel matter along the filaments and contribute to the web's ongoing evolution. The cosmic web reminds us that empty space isn't truly empty. It's structured by invisible forces and filled with diffuse matter. It teaches us that separation is often an illusion, that connections exist even across the vastest cosmic distances. In the silent framework of the cosmos, we find not chaos but pattern, not randomness but structure. In the intricate tapestry of subatomic particles, neutrinos stand apart as nature's most elusive wanderers. Nearly massless and carrying no electrical charge, these ghostly particles travel through the cosmos at nearly the speed of light, passing effortlessly through planets, stars, and even entire galaxies. At this very moment, trillions of neutrinos are streaming through your body, yet you feel nothing. They rarely interact with ordinary matter, preferring instead to maintain their spectral journey across the universe. The story of neutrinos begins in the early 20th century with a puzzle. When scientists studied radioactive decay, they noticed that energy seemed to disappear during certain nuclear reactions. This apparent violation of energy conservation troubled physicists deeply. In 1930, Wolfgang Pauli proposed a radical solution. The missing energy was being carried away by an unknown particle, one so elusive it had escaped detection. Enrico Fermi later named this hypothetical particle the neutrino, meaning little neutral one in Italian. For decades, neutrinos remained theoretical, mathematically necessary but observationally absent. It wasn't until 1956 that Frederick Rhines and Clyde Cowan finally detected these ghost particles by measuring the distinctive signals produced when neutrinos occasionally interact with protons. Their experiment, conducted near a nuclear reactor, a prolific source of neutrinos, confirmed Pauli's audacious proposal and earned Reiners the Nobel Prize. We now know that neutrinos come in three flavors: electron neutrinos, Moore neutrinos, and tau neutrinos, each associated with a corresponding charged particle. But in a quantum twist that defies classical intuition, neutrinos can change from one flavor to another as they travel through space, a phenomenon called neutrino oscillation. This transformation, confirmed by experiments in the late 20th century, proved that neutrinos must have mass, albeit incredibly small, less than 1/1,000,000th the mass of an electron. The cosmos creates neutrinos through various processes. The most abundant source is our Sun, which produces an astonishing number of electron neutrinos. About 65 billion per square centimeter per second reach Earth, as a byproduct of the nuclear fusion reactions that power it. These solar neutrinos give us a direct glimpse into the Sun's core, a region otherwise hidden from view by layers of superheated gas. More dramatic cosmic events generate even more energetic neutrinos. When massive stars collapse and explode as supernovae, they release a brief but intense burst of neutrinos carrying away most of the explosion's energy. In fact, neutrinos from supernova. 1987. A reached Earth several hours before its light became visible. The light was trapped within the exploding star, while neutrinos streamed directly through the stellar material. The most energetic neutrinos of all come from active galactic nuclei, where supermassive black holes devour surrounding matter, and from cosmic ray interactions in the atmosphere of our own planet. These high-energy neutrinos can have energies millions of times greater than those produced in our most powerful particle accelerators on Earth. Earth itself produces neutrinos through the natural radioactive decay of elements like uranium and thorium in its crust and mantle. These geoneutrinos provide unique information about our planet's interior composition and the heat sources that drive geological processes. Human activities add to this neutrino symphony. Nuclear reactors are prolific sources, producing electron antineutrinos, the antimatter counterparts to electron neutrinos. As uranium and plutonium atoms split, particle accelerators generate controlled beams of neutrinos for experimental study. In a sense, we have become participants in the cosmic neutrino narrative, adding our own notes to this ethereal chorus. To observe these ghostly particles, scientists have built some of the most extraordinary detectors on Earth. Deep underground, shielded from cosmic rays and other interference, enormous tanks wait patiently for the rare interactions between neutrinos and atoms of water or other materials. The Super Kamiokande detector in Japan contains 50,000 tons of ultra-pure water surrounded by thousands of light sensors. When a neutrino interacts with a water molecule, it creates a charged particle that travels faster than light can move through water, though still slower than light in vacuum. This creates a cone of light called Cherenkov radiation, the optical equivalent of a sonic boom, which the sensors detect. Even more ambitious is the IceCube Neutrino Observatory at the South Pole. Rather than building a tank, IceCube uses a cubic kilometer of the Antarctic ice sheet as its detection medium. Thousands of optical sensors embedded in the ice monitor for the telltale flashes of blue light that indicate a neutrino interaction. This frozen observatory specially targets high-energy neutrinos from violent cosmic events, providing information about some of the most energetic phenomena in the universe. In the Mediterranean Sea, the Antares and upcoming KM3 net detectors use the deep ocean as their detection medium, while in Siberia, the Baikal Deep Underwater Neutrino Telescope performs a similar function in the world's deepest lake. Other detectors use tanks of liquid argon, gallium, or other materials, each optimized for different neutrino energies or sources. Why devote such extraordinary resources to catching particles that barely interact with matter? The answer lies in neutrinos' unique properties as cosmic messengers. Unlike light, which can be blocked or scattered, and unlike cosmic rays, which are deflected by magnetic fields, neutrinos travel in straight lines from their source to Earth, carrying unaltered information across vast cosmic distances. This makes neutrinos invaluable for studying objects and regions that are otherwise hidden from view. Neutrinos from the Sun's core reach us without modification, providing direct information about the nuclear reactions powering our star. Neutrinos from distant supernovae carry details about the explosion mechanism and the formation of neutron stars or black holes. And high-energy cosmic neutrinos can reveal the workings of the most powerful particle accelerators in the universe: active galactic nuclei and gamma-ray bursts. The study of neutrinos has repeatedly forced scientists to revise their understanding of particle physics. The discovery of neutrino oscillation and mass challenged the Standard Model, the otherwise highly successful theory of subatomic particles. Some theorists suggest that neutrinos might be their own antiparticles, a possibility with profound implications for understanding matter-antimatter asymmetry in the universe. Cosmologists study neutrinos for another reason, as relics from the Big Bang. Similar to the cosmic microwave background radiation, but even older, the cosmic neutrino background consists of neutrinos produced during the first second after the Big Bang. These primordial particles, cooled by cosmic expansion to extremely low energies, permeate the universe with a density of about 340 neutrinos per cubic centimeter. Though not yet directly detected due to their low energy, these ancient messengers would provide unprecedented insight into the earliest moments of cosmic history. Neutrinos may also hold clues to one of the greatest mysteries in physics: the nature of dark matter. While most evidence suggests dark matter consists of a yet undiscovered particle, some theories propose that sterile neutrinos, hypothetical cousins to the known neutrino types that interact solely through gravity, might contribute to the universe's dark matter content. The discovery of neutrinos reminds us that the universe often communicates in whispers rather than shouts. These nearly massless particles, invisible to conventional observation, carry crucial information across cosmic distances. Their story encourages scientific humility, the recognition that what we cannot easily detect may be as important as what we can. As technology advances, neutrino astronomy grows increasingly sophisticated. Future detectors will be even larger and more sensitive, capable of observing fainter signals from more distant sources. Networks of detectors around the globe will work together to pinpoint neutrino sources with unprecedented precision, potentially unveiling cosmic phenomena currently unknown to science. In their ghostly passage through the cosmos, neutrinos embody a profound paradox. Particles that barely exist in conventional terms, with nearly zero mass and almost no interactions, nevertheless play crucial roles in stellar physics, cosmic evolution, and our understanding of fundamental forces. They remind us that emptiness itself is more complex and information-rich than we might assume. Imagine the emptiest place you can. Remove all air molecules, all dust particles, all atoms and ions. Shield it from every ray of light, every form of radiation. Cool it to absolute zero, removing all thermal energy. What remains? According to classical physics, the answer is simple: nothing at all. A perfect void, an absolute absence, the purest embodiment of emptiness. But quantum physics tells a dramatically different story. The vacuum, supposedly empty space, seethes with activity. Particles and their antimatter counterparts spontaneously appear and annihilate each other in an endless dance. Fields fluctuate around their lowest energy states. Space itself buzzes with a baseline energy that can never be removed. In the quantum world, nothing is not nothing. This concept of the quantum vacuum represents one of the most profound conceptual revolutions in modern physics. The vacuum isn't merely the absence of things. It is a something, a physical system with properties and behaviors all its own. It is, in a very real sense, the foundation upon which all else in our universe is built. The first clue to the vacuum's hidden nature came from a phenomenon called vacuum fluctuations. According to Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, there are fundamental limits to how precisely we can know certain pairs of physical properties simultaneously. One such pair is energy and time. We cannot know exactly how much energy is present in a system for an infinitesimally short duration. This uncertainty allows something remarkable to happen in supposedly empty space. Energy can be borrowed from the vacuum for extremely brief periods, manifesting as pairs of particles that pop into existence and then annihilate each other almost immediately. These are not metaphorical particles or mathematical constructs, but real particles: electrons, photons, quarks, albeit with extremely short lifespans. Physicists call these ephemeral entities virtual particles, to distinguish them from the stable particles we typically observe. Like ghostly apparitions, they flicker in and out of existence, leaving only subtle traces of their presence. The vacuum is thus a frothing quantum foam of appearing and disappearing particles, a cosmic effervescence that occurs everywhere in the universe, even in the darkest, coldest reaches of intergalactic space. This isn't merely a theoretical curiosity. These vacuum fluctuations have measurable effects on the physical world. One of the most striking demonstrations is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed decades later. The experiment is deceptively simple. Two uncharged metal plates are placed extremely close together in a vacuum. Classical physics predicts no force between them, yet they attract each other with a force that increases as the gap narrows. Why? Because the tiny space between the plates restricts which virtual particles can momentarily appear there. Fewer types of particles can fit between the plates than in the surrounding space, creating a pressure difference that pushes the plates together. The Casimir effect provides tangible evidence that the vacuum is not empty, but filled with virtual particles and quantum fluctuations. It confirms that the zero-point energy, the lowest possible energy a quantum system can have, is not zero at all, but a positive value that pervades all of space. Another manifestation of the quantum vacuum's activity appears in the behavior of real particles. Electrons, for instance, are constantly emitting and reabsorbing virtual photons, creating a cloud of these fleeting particles that surrounds them. This process, called vacuum polarization, slightly alters the electron's properties from what a bare electron would display. What we measure in laboratories isn't the pure fundamental electron, but this composite entity, an electron dressed in its cloud of virtual particles. Perhaps most remarkably, the vacuum itself can be polarized. In intense electric fields, virtual electron-positron pairs can be briefly separated before they annihilate. In extremely strong fields, such as those around neutron stars or in powerful laser facilities, the vacuum can actually break down, and real electron-positron pairs can be created from nothing but pure energy. Following Einstein's famous equation, E is equal to mc squared. The quantum vacuum also helps explain the Lamb shift, a tiny difference in energy levels of electrons in hydrogen atoms that couldn't be accounted for by earlier quantum theories. The interaction between electrons and the fluctuating vacuum fields causes this shift, providing further evidence of the vacuum's dynamic nature. Even the magnetic properties of elementary particles, their so-called magnetic moments, are influenced by virtual particles from the vacuum. The measured values differ slightly from theoretical predictions that ignore vacuum effects, and the difference matches precisely what quantum field theory predicts when vacuum fluctuations are included. These phenomena highlight a profound truth. What we perceive as empty space is actually a complex, structured medium. It is not the absence of fields, but rather fields in their lowest energy state, a state that is not zero but has a positive energy density. Physicists call this the vacuum energy density, or zero-point energy. The concept extends beyond the laboratory to cosmic scales. Some theories suggest that the mysterious dark energy accelerating the universe's expansion might be related to vacuum energy. If space itself contains energy, as quantum field theory suggests, then as the universe expands, more space means more energy, creating a repulsive force that drives cosmic acceleration. However, this connection between vacuum energy and dark energy presents a major puzzle. Quantum field theory predicts a vacuum energy density approximately 120 orders of magnitude larger than what astronomical observations of cosmic acceleration suggest. This discrepancy, called the cosmological constant problem, represents one of the greatest unsolved mysteries in modern physics. Why is the vacuum energy so much smaller than our best theories predict? The quantum vacuum also played a crucial role in the very early universe. During cosmic inflation, a period of exponential expansion shortly after the Big Bang, the universe was dominated by vacuum energy. This special state, called a false vacuum, contained enormous energy that drove space to expand at a breathtaking rate, doubling in size every tiny fraction of a second. Some theoretical physicists suggest that vacuum fluctuations might even give birth to entire universes. In these scenarios, tiny quantum fluctuations in the vacuum could, through gravitational effects, create expanding bubbles that develop into new cosmic domains, daughter universes budding from our own. While speculative, such ideas highlight the creative potential hidden within seemingly empty space. The quantum vacuum challenges our intuitive understanding of nothingness. In everyday language, we use nothing to mean an absence, a void, a lack. But in quantum physics, nothing is always something, a vibrant, fluctuating foundation from which everything else emerges. This reframing of emptiness resonates beyond physics. Ancient philosophical traditions, from Buddhist concepts of emptiness to Taoist notions of the void, have long suggested that nothingness is not mere absence, but a fertile ground of potential. Modern quantum physics lends scientific weight to these intuitions, revealing the vacuum as a plenum, a fullness, rather than a void. For all its strangeness, the quantum vacuum is not separate from the world we experience. It is the canvas upon which all matter is painted, the stage upon which all physical processes play out. Every atom in our bodies, every photon of light, every galaxy in the cosmos exists against this background of quantum fluctuations and zero-point energy. When we contemplate the stars at night, we typically focus on what is there, the pinpoints of light against the darkness. But quantum physics reminds us that the darkness itself is worthy of wonder. The apparent emptiness between stars and galaxies contains the seeds of being, the potential for existence, the substrate from which everything we know emerges and to which it will eventually return. For most of human history, we have explored the cosmos exclusively through light. The visible glow of stars, the infrared warmth of distant clouds, the radio whispers of far-off galaxies. But light can only tell us so much. It gets blocked by dust, distorted by intervening matter, and some cosmic objects emit no light at all. What if there were another way to perceive the universe? One that relied not on electromagnetic radiation, but on the very fabric of space-time itself. This alternative view of the cosmos became possible on September 14, 2015, when scientists detected gravitational waves for the first time. Ripples in the fabric of space-time created by the violent collision of two black holes 1.3 billion light-years away. This momentous discovery, coming almost exactly 100 years after Albert Einstein first predicted their existence, opened an entirely new window onto the universe. Einstein's general theory of relativity, published in 1915, reimagined gravity not as a force acting across space, but as a consequence of space, more precisely space-time, being curved by the presence of mass and energy. Just as a bowling ball placed on a trampoline creates a depression that smaller balls will roll towards, massive objects like stars and planets curve the space-time around them, causing other objects to follow curved paths we interpret as gravitational attraction. This revolutionary theory led to a remarkable prediction. If massive objects move in certain ways, especially if they accelerate asymmetrically, they should create ripples in space-time that propagate outward at the speed of light. These gravitational waves would stretch and compress space itself as they pass through, alternately increasing and decreasing the distances between objects by tiny amounts. The challenge in detecting these waves lies in their extraordinary subtlety. By the time gravitational waves from cosmic events reach Earth, they typically change distances by less than the width of a proton, one of the smallest particles in an atom. Measuring such minute distortions requires instruments of exceptional precision. The breakthrough came with the Laser Interferometer Gravitational Wave Observatory, or LIGO. This remarkable facility consists of two detector sites separated by 3,000 kilometers, one in Hanford, Washington, and the other in Livingston, Louisiana. Each detector features two 4-kilometer-long vacuum tubes arranged in an L shape, with powerful lasers bouncing between mirrors at their ends. When a gravitational wave passes through Earth, it momentarily stretches space in one direction while compressing it in the perpendicular direction. This changes the relative lengths of the two arms of the L-shaped detectors by a tiny amount, which creates a distinctive interference pattern in the laser light. By comparing signals between the two widely separated detectors, scientists can confirm that they've observed a true gravitational wave rather than local vibrations or noise. The first detected gravitational wave, designated GW150914, came from the final orbits and merger of two black holes, with masses about 36 and 29 times that of our Sun. As these immense objects spiraled toward each other, they accelerated to roughly half the speed of light, warping the surrounding space-time so violently that ripples radiated outward across the cosmos. By the time these ripples reached Earth, they were incredibly faint, yet LIGO's extraordinary sensitivity allowed it to record the event. The signal, when converted to sound, produced a characteristic chirp, a rising tone that suddenly stops when the black holes merge. This gravitational symphony carried precise information about the masses of the black holes, their distances, and even how fast they were spinning. Since that first detection, dozens more gravitational wave events have been observed. Most involve pairs of black holes, but in August 2017, scientists detected gravitational waves from a different source, the collision of two neutron stars. Unlike black hole mergers, which are expected to produce little or no electromagnetic radiation, neutron star collisions release tremendous amounts of light across the spectrum. Within seconds of detecting this gravitational wave signal, astronomers around the world pointed their telescopes toward its source, capturing the resulting explosion, called a kilonova, invisible light, X-rays, gamma rays, radio waves, and infrared. This event, known as GW170817, marked the dawn of multi-messenger astronomy, the ability to study cosmic events through both gravitational waves and light. The neutron star collision revealed something else remarkable. These stellar cataclysms forge heavy elements like gold, platinum, and uranium. The spectra from the kilonova showed signatures of these newly created elements being flung into space. The gold in your jewelry and the uranium powering nuclear plants likely originated in similar cosmic collisions billions of years ago. Gravitational waves travel unimpeded through matter that would block light. They are neither scattered nor absorbed as they journey across the cosmos, carrying pristine information about their sources. This makes them ideal messengers from regions that are otherwise hidden from view, like the interiors of supernovae, the neighborhoods around supermassive black holes, or even the first fraction of a second after the Big Bang. Unlike light, which can only come from matter, like stars or hot gas, gravitational waves are generated by the movement of mass itself. This allows us to directly observe objects that emit little or no electromagnetic radiation, most notably black holes. Before gravitational wave astronomy, black holes could only be studied indirectly through their effects on surrounding matter. Now we can hear them directly as they spiral together and merge. The analogy to sound is apartment. While light shows us a series of snapshots of the universe, gravitational waves let us hear its dynamic processes unfold, its crashes, collisions, and symphonic movements. If traditional astronomy is like seeing a drum, gravitational wave astronomy is like hearing it being played. The types of gravitational waves we can currently detect come from especially violent cosmic events, colliding black holes and neutron stars. But in principle, any asymmetric acceleration of mass generates these space-time ripples. The Earth orbiting the Sun produces gravitational waves, as do you when you wave your arm. They're just far too feeble to detect with current technology. More sensitive detectors are being developed to capture a wider range of gravitational wave frequencies. The European Space Agency is planning a space-based gravitational wave observatory called LISA, Laser Interferometer Space Antenna, which will detect lower frequency waves from sources like supermassive black hole mergers and compact binary systems in our galaxy. Scientists are also developing techniques to use arrays of pulsars, rapidly spinning neutron stars that emit regular radio pulses, as enormous gravitational wave detectors spanning the galaxy. These advances promise to reveal entirely new classes of gravitational wave sources. We might detect the background hum of countless distant events blending together, similar to the ambient noise in a crowded restaurant. We might hear the gravitational waves produced during cosmic inflation, carrying information about the universe when it was just a fraction of a second old. We might even detect exotic phenomena like cosmic strings, hypothetical defects in space-time left over from the Big Bang. The birth of gravitational wave astronomy represents more than just a new observational technique. It fundamentally changes our relationship with the cosmos. For all of human history, we have been limited to studying the universe through light and other forms of electromagnetic radiation. Now we can directly sense the rhythmic breathing of space-time itself, feeling the pulse of distant cosmic catastrophes through the most fundamental fabric of reality. This ability to detect gravitational waves also provides a powerful confirmation of Einstein's general relativity. The observed wave patterns precisely match what his theory predicts, even under the extreme conditions of black hole mergers, where gravity reaches its most intense expression. Each new detection offers an opportunity to test whether gravity behaves exactly as Einstein described, or whether subtle deviations might point toward new physics. Perhaps most profoundly, gravitational waves remind us that space itself is a dynamic entity, not a static stage upon which cosmic drama unfolds, but an active participant in that drama. Space stretches, compresses, warps, and ripples. It carries energy and information across the cosmos. It connects distant events through invisible vibrations that pass through everything, including our own bodies, linking us directly to the most violent and energetic processes in the universe. As we continue to refine our ability to detect these subtle cosmic messengers, we will undoubtedly encounter phenomena we never imagined. Just as radio astronomy revealed pulsars and quasars, and infrared astronomy unveiled dust-enshrouded stellar nurseries, gravitational wave astronomy will likely uncover entirely new classes of objects and events, things that cannot be seen but can be felt through their gravitational signature. In a universe largely invisible to our eyes, filled with dark matter, dark energy, and black holes, gravitational waves offer a new form of perception, one that does not rely on light, but on the trembling of reality itself. They allow us to sense directly what was previously known only through its gravitational effects, to hear the universe rather than merely see it. The universe we directly experience unfolds in 4 dimensions, 3 of space, up, down, left, right, forward, backward, and 1 of time. This 4-dimensional framework has served physics well, from Newton's laws to Einstein's relativity. But what if our universe contains more dimensions than the ones we perceive? What if our cosmos is just one among many in a vast multiverse? These questions, once firmly in the realm of science fiction, have become serious scientific inquiries driven by attempts to reconcile quantum mechanics with gravity and to explain the peculiar fine-tuning of our universe's fundamental constants. String theory represents the most mathematically developed approach to these questions. This ambitious framework attempts to unify all fundamental forces and particles by replacing the concept of point-like particles with tiny vibrating strings. The different vibration patterns of these strings would give rise to different particles: electrons, quarks, photons, and all the rest. But string theory contains a surprising requirement. For the mathematics to work consistently, the universe must have more dimensions than the 4 we experience. The standard version of string theory requires 10 dimensions, 9 of space and 1 of time. More complex variations like M theory suggest 11 dimensions. But if these extra dimensions exist, why don't we notice them in everyday life? The most common explanation is that these additional dimensions are compactified, curled up into incredibly tiny loops on the order of 10 to the negative 33 centimeters, far smaller than anything we can directly observe. Every point in our familiar space would contain these tightly wound extra dimensions, like an infinitesimal origami hidden within the fabric of reality. Think of an ant walking along a garden hose. From far away, the hose appears to be a one-dimensional line. Only as we zoom in do we see that the hose has a second dimension wrapped around its length, its circular cross-section. Similarly, our universe might have additional spatial dimensions coiled up at every point, too small for us to notice under normal circumstances. The shape and structure of these hidden dimensions, what mathematicians call their topology, would determine the properties of particles and forces in our observable universe. Different configurations would result in different physical laws. This insight led to the realization that string theory doesn't predict a unique universe, but rather a vast landscape of possible universes, each with its own physical constants and particles. The mathematics of these compact dimensions is extraordinarily complex. The simplest compact spaces are called Calabi-Yau manifolds, 6-dimensional geometric structures with intricate properties. Different Calabi-Yau shapes would give rise to different physics in our 4-dimensional world. Some would create universes with exotic particles unknown to our physics. Others might produce worlds where electromagnetism is stronger or weaker than in our universe. Still others might not allow stable atoms to form at all. String theorists have calculated that there could be as many as 10 to the 500th power different possible configurations for these extra dimensions, an unimaginably vast number that dwarfs the approximately 10 to the 80th power atoms in the observable universe. Each configuration would correspond to a different set of physical laws and constants. Another approach to higher dimensions comes from brane world scenarios, from membrane. Other branes might exist parallel to ours, possibly with their own galaxies, stars, and forms of life, all invisible to us because they occupy different positions in the extra dimensions. In some brane world models, gravity can leak into the extra dimensions, explaining why it appears so much weaker than the other fundamental forces. This leakage would become noticeable only at very small distances or very high energies, potentially observable in particle accelerators like the Large Hadron Collider, or in precise measurements of gravity at submillimeter scales. The Randall-Sundrum model, proposed by physicists Lisa Randall and Raman Sundrum, suggests that a fifth dimension might be warped, stretched or compressed in different regions. This warping could make the extra dimension effectively infinite in size while still remaining hidden from our direct observation. In this scenario, gravity would be naturally concentrated on our brane while being able to propagate through the bulk, potentially resolving long-standing puzzles in particle physics. If extra dimensions exist, they might occasionally reveal themselves. Particles or radiation might sometimes travel through the higher dimensional bulk, disappearing from our brane and reappearing elsewhere, an effect that would appear to violate conservation laws. Or microscopic black holes might form at energies much lower than expected in a purely four-dimensional universe, potentially detectable in cosmic ray collisions or future particle accelerators. Some theorists have even suggested that dark matter, the invisible substance that appears to hold galaxies together, might be ordinary matter residing on a parallel brane, invisible to us except through its gravitational effects that can propagate through the bulk. Similarly, the mysterious dark energy accelerating the universe's expansion might be a manifestation of how our brane interacts with others, or with the bulk itself. The concept of hidden dimensions naturally extends to the idea of a multiverse, the hypothesis that our universe is just one among many. Several different multiverse concepts have emerged from modern physics, each arising from different theoretical considerations. The inflationary multiverse arises from cosmic inflation, the theory that our universe underwent a period of exponential expansion shortly after the Big Bang. According to this view, inflation doesn't stop everywhere at once. Some regions stop inflating and form bubble universes, while inflation continues elsewhere, constantly generating new bubbles. These bubble universes could have different physical properties, effectively creating a vast ensemble of distinct cosmos. Cosmologist André Linde, one of inflation's pioneers, compares this process to a cosmic fractal, with new universes endlessly budding from expanding space. Each bubble universe would be causally disconnected from the others. Events in one cannot influence events in another, because they're separated by regions of space that are still inflating at fantastic speeds, pushing them apart faster than light could connect them. Another concept is the quantum multiverse, stemming from certain interpretations of quantum mechanics. In the many worlds interpretation, first proposed by physicist Hugh Everett in 1957, every quantum event causes reality to branch into multiple histories that all exist in parallel. A particle that could be measured as spinning up or down would actually do both, creating two branches of reality that subsequently evolve independently. If true, this would create an almost unimaginably vast multiverse of parallel realities differing initially by just the outcome of quantum events. In the many-worlds scenario, all possible histories exist simultaneously, some nearly identical to our experienced reality, others wildly different based on how quantum probabilities have played out. There would be universes where dinosaurs never went extinct, where Earth formed with slightly different conditions, or where the fundamental constants of physics vary subtly from our own. String theory's landscape of possible universes, combined with eternal inflation, suggests a string theory multiverse containing perhaps 10 to the 500th power different possible universes, each with its own physical laws. With so many possibilities, universes capable of supporting life would exist simply as a matter of probability, even if they represent a tiny fraction of the total. A more speculative multiverse concept comes from mathematician Max Tegmark, who proposed a four-level hierarchy of increasingly encompassing multiverse types. At the highest level, Tegmark suggests that any mathematically consistent structure that could describe a universe must exist as a physical reality somewhere in the multiverse. This mathematical multiverse would contain not just variations on our physics, but entirely different mathematical frameworks for reality itself. The idea of a multiverse helps address one of the most perplexing questions in modern physics. Why do our universe's fundamental constants appear fine-tuned for life? From the strength of the electromagnetic force, to the mass of the electron, to the energy of the vacuum, numerous parameters seem precisely calibrated to allow for complex structures like stars, planets, and eventually, living organisms. Change any of these values slightly, and the universe becomes hostile to complexity. Stars wouldn't form, or they'd burn out too quickly. Chemistry would be impossible. Atoms themselves might be unstable. This apparent fine-tuning has led some to invoke a creator or designer, but the multiverse offers a different explanation. If a vast multiverse exists with varying physical laws, we shouldn't be surprised to find ourselves in one of the rare universes compatible with our existence. This is an application of the anthropic principle, the idea that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We can only observe universes compatible with our existence, regardless of how rare such universes might be within the larger multiverse. An analogy would be a person marveling at how perfectly their environment suits human life, without realizing they're in a nature preserve specifically designed for human habitation, surrounded by vast uninhabitable regions. From within the habitable zone, the world might seem miraculously fine-tuned, but this perception comes from a selection effect. Humans can only exist in the places suited for them. The anthropic principle comes in different forms. The weak anthropic principle simply states that what we observe must be compatible with our existence as observers. The strong anthropic principle makes the more controversial claim that the universe must have properties allowing life to develop, because it requires observers. These distinctions reflect different philosophical interpretations of the relationship between consciousness and cosmic structure. While mathematically elegant, these ideas about hidden dimensions and multiple universes face a significant challenge: finding observable evidence. Science traditionally progresses through empirical testing, but how can we test hypotheses about realms fundamentally disconnected from our direct experience? Some potential tests do exist. If our universe once collided with another bubble universe, it might have left subtle patterns in the cosmic microwave background radiation. Certain anomalies in this ancient light, like the cold spot observed by the Planck satellite, have been speculatively attributed to such inter-universal interactions. For extra dimensions, the energy needed to excite particles into these hidden dimensions might be accessible in particle accelerators. The detection of certain particles predicted by supersymmetry, a theory often associated with string theory, would provide indirect support for these ideas. Precision tests of gravity at very small distances might reveal deviations from Newton's inverse square law, suggesting gravity is leaking into extra dimensions. Similarly, careful measurements of high-energy cosmic rays might detect evidence of microscopic black holes or other phenomena predicted by higher dimensional theories. Quantum gravity theories that incorporate extra dimensions also make predictions about the polarization of gravitational waves. Future gravitational wave observatories might be sensitive enough to detect these subtle effects, providing evidence for or against specific higher dimensional models. Ultimately, the multiverse concept challenges our notion of what constitutes a scientific theory. Some critics argue that without directly testable predictions, multiverse theories venture into metaphysics rather than physics. Others counter that indirect evidence and mathematical consistency can still make these ideas scientifically valuable, even if they push the boundaries of what we traditionally consider science. Philosopher Karl Popper famously argued that scientific theories must be falsifiable, capable of being proven wrong by observation or experiment. Some physicists worry that multiverse theories, by potentially explaining any possible observation, become unfalsifiable and therefore unscientific. Others argue that the multiverse isn't a single theory, but a consequence of other theories, like inflation or string theory, that are themselves scientifically testable. The debate touches on deep questions about the nature of scientific explanation itself. Is a theory successful if it explains why things are as we observe them? Or must it also predict specific observations that would be different if the theory were false? The multiverse forces us to reconsider what we mean by explanation in science. What's clear is that these ideas reflect our deepening understanding of the cosmos. Just as Copernicus showed that Earth is not the center of the universe, and Edwin Hubble revealed that our galaxy is just one among billions, the multiverse concept suggests our entire observable universe may be a tiny fraction of a much larger reality. This progression represents a kind of cosmic humility. Each new discovery has revealed that what we once thought was everything is merely a small part of a greater whole. Perhaps our observable universe, vast as it seems, is just one bubble in an ocean of cosmic possibilities, one manifestation of the infinite creative potential of existence itself. Whether these hidden dimensions and parallel universes ultimately prove to be physical realities or useful mathematical constructs, they represent humanity's continuing quest to understand reality at its most fundamental level, to peer beyond appearances into the deepest structures of existence itself. If our universe is but one thread, how many others lie beyond the veil? As our cosmic journey nears its end, we turn our gaze forward, not just to the future of our exploration, but to the future of the invisible universe itself. What fate awaits the cosmos in the distant future? How will dark energy shape the evolution of space? What new tools and techniques might pierce the veil of invisibility that shrouds so much of existence? These questions invite us to extend our imagination across vast stretches of time and possibility. The long-term destiny of our universe appears to be governed primarily by dark energy, that mysterious force accelerating cosmic expansion. If dark energy maintains its current properties, as most observations suggest, the universe faces a future of ever-increasing isolation. Galaxies outside our local group will recede beyond our cosmic horizon, their light stretched to invisibility by the expanding space between us. After about 100 billion years, even the nearest external galaxies will fade from view, and observers in the Milky Way, by then merged with Andromeda, would see only a single island of stars in an otherwise empty cosmos. This scenario, often called the Big Freeze or heat death, continues with the gradual extinction of stellar light. Stars exhaust their nuclear fuel and flicker out. New star formation eventually ceases as gas supplies dwindle. The universe grows increasingly dark and cold, populated primarily by the cooling remnants of former stars, white dwarfs, neutron stars, and black holes. Even these seemingly eternal objects face eventual dissolution. Over unimaginably long timescales, 10 to the 100th power years and beyond, quantum effects come into play. Protons, once thought stable, might decay into lighter particles. Black holes slowly evaporate through Hawking radiation, returning their mass energy to a universe with fewer and fewer ways to use it. Eventually, even the most stable particles may decay, leaving a diffuse soup of elementary particles and radiation in a state of maximum entropy, a universe where nothing meaningful can happen because all energy has been evenly distributed. This rather bleak scenario assumes dark energy remains constant, but what if it doesn't? In this scenario, the accelerating expansion becomes so powerful that it eventually overcomes all other forces. Galaxies would be torn apart, followed by solar systems, planets, atoms, and finally the fabric of space-time itself. Everything would be ripped asunder as infinite expansion is reached in finite time. The universe would collapse back on itself, temperatures and densities would soar, and all structure would be compressed into an infinitesimal point, perhaps seeding another Big Bang and a new cycle of cosmic evolution. A variation on this theme proposes a Big Bounce, where the universe oscillates through successive cycles of expansion and contraction, each bounce potentially giving rise to different physical laws. Some theories suggest we might be living in just one cycle of an eternally pulsating cosmos, its heartbeat measured in trillions of years. These scenarios might seem distant and abstract, relevant only on timescales far beyond human experience. Yet they connect deeply to questions we're investigating now: the nature of dark energy, the properties of the Higgs field, the stability of the vacuum state. All these cutting-edge research areas directly inform our understanding of cosmic destiny. Long before any of these ultimate fates unfold, our ability to observe and understand the invisible universe will likely transform through new technologies and theoretical breakthroughs. Already, next-generation observatories promise to reveal aspects of the cosmos currently hidden from view. The James Webb Space Telescope, successor to the Hubble Space Telescope, peers into the universe with unprecedented infrared sensitivity. This allows it to see through cosmic dust clouds, observe the earliest galaxies formed after the Big Bang, and directly image exoplanets around nearby stars. Its ability to analyze the chemical composition of distant atmospheres might even detect biosignatures, potential evidence of life beyond Earth. The Euclid mission, launched by the European Space Agency, is mapping the distribution of dark matter across 2 billion galaxies, creating the most detailed three-dimensional map of the invisible universe. By precisely measuring how cosmic structure has evolved over time, Euclid helps constrain the properties of dark energy and test alternative theories of gravity. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned for the 2030s, will detect gravitational waves at frequencies inaccessible to ground-based detectors. This opens a window onto entirely new classes of events, from the mergers of supermassive black holes to the spiraling dance of binary star systems in our galaxy. LISA might even detect the gravitational wave background left over from the Big Bang itself, the oldest signal in the universe. On Earth, enormous neutrino detectors like Hyper Kamiokande in Japan and DUNE, Deep Underground Neutrino Experiment in the United States, will capture neutrinos with unprecedented precision. These ghost particle observatories might solve remaining mysteries about neutrino properties, detect neutrinos from distant supernovae, and possibly even find the elusive cosmic neutrino background, relics from just 1 second after the Big Bang. New dark matter detectors push the boundaries of sensitivity, using everything from liquid xenon to supercooled crystals to bubble chambers. Each new generation improves our chances of directly detecting dark matter particles, if they exist in forms we can interact with. Meanwhile, particle accelerators probe ever higher energies, potentially producing dark matter particles, or revealing new physics that might explain dark matter's properties. Quantum technologies, computing, sensing, and communication promise entirely new approaches to understanding the invisible cosmos. Quantum computers might simulate complex quantum systems that classical computers cannot handle, from the behavior of exotic materials to the quantum properties of black holes and the early universe. Quantum sensors achieve precision far beyond classical limits, enabling new types of measurements that could reveal subtle effects of dark matter or extra dimensions. Theoretical physics continues its quest for a theory of everything that would unite quantum mechanics and general relativity. String theory, loop quantum gravity, causal set theory, and other approaches offer different visions of the fundamental nature of space, time, and matter. While a complete unified theory remains elusive, each approach provides insights that shape our understanding of the invisible aspects of the universe. Artificial intelligence increasingly assists in this cosmic quest, identifying patterns in vast datasets that human researchers might miss. Machine learning algorithms sift through petabytes of astronomical data, identifying gravitational lenses, classifying galaxies, and flagging unusual objects for human attention. AI helps simulate complex physical systems, optimize detector designs, and even suggest new theoretical approaches to long-standing problems. Beyond these technological and theoretical advances, our conceptual framework for understanding the invisible universe continues to evolve. The history of science teaches us that paradigm shifts often occur when least expected. Just as quantum mechanics and general relativity revolutionized physics in the early 20th century, future insights might completely transform our understanding of dark matter, dark energy, cosmic origins, and ultimate fates. Perhaps most intriguingly, the boundary between the visible and invisible continues to shift. What was once undetectable becomes observable with new instruments and techniques. What was once theoretical becomes empirical. The invisible doesn't necessarily remain so forever. It often represents the frontier of our knowledge, the edge of our technological capabilities, the horizon of our understanding. This progressive unveiling of the cosmos reflects a deeper human pattern. Throughout history, We have moved from seeing ourselves at the center of a small universe to recognizing that we occupy a modest planet orbiting an ordinary star in one galaxy among billions. Each discovery has decentered us physically while expanding us conceptually. We are small within the cosmos, but great in our capacity to comprehend it. The invisible universe, dark matter, dark energy, extra dimensions, quantum fluctuations, reminds us that reality extends far beyond our direct perception. What we see is merely the surface of a much deeper truth. The universe we observe with our eyes comprises just 5% of cosmic reality. The rest remains hidden, mysterious, invisible, yet increasingly knowable through the combined power of human imagination, mathematics, and technology. In the silent spaces between stars, in the invisible scaffolding shaping galaxies, in the quantum foam underlying space-time itself, we find not emptiness but fullness, not absence but presence. The invisible universe isn't nothing, it's almost everything. And in exploring it, we discover not just the cosmos, but ourselves, creatures of stardust with minds capable of contemplating darkness and finding within it the subtle glow of understanding. As we continue this exploration, we remain humble before the vastness of what remains unknown. Each answer generates new questions. Each discovery reveals new mysteries. The invisible universe is not a problem to be solved, but a reality to be uncovered, layer by layer, in a journey without end. We are still in the infancy of our understanding. As our journey through the invisible universe comes to an end, we find ourselves returned to the silent spaces between stars, to the quiet mystery with which we began. We have traveled far, through dark matter halos and across the cosmic web, into the hearts of black holes and along the ripples of gravitational waves, down to the quantum foam of space-time, and perhaps even to the thresholds of other universes. Yet, for all we've explored, the invisible universe remains largely unknown. Like deep-sea divers who have glimpsed only the uppermost layers of an abyssal trench, we have barely begun to fathom the depths of cosmic reality. This incompleteness is not a failure, but an invitation, a summons to deeper wondering, to more refined questioning, to continued exploration. The history of science teaches us that today's mysteries often become tomorrow's understanding, that what seems impenetrable darkness frequently harbors undiscovered illumination. The invisible universe speaks to us, not through light, but through other languages. The gravitational pull that shapes galaxies, the quantum probabilities that underlie particles, the geometric curvature of space-time itself. Learning to listen to these subtle voices requires not just new instruments, but new ways of thinking, new metaphors, new mathematics. Perhaps most profoundly, the invisible universe reminds us of the limits of our perception. Our senses evolved to navigate a tiny corner of reality, the middle scales, where neither quantum effects nor cosmic expanses dominate. That we can comprehend realms far beyond our direct experience is a remarkable achievement of the human mind, a testament to our capacity to transcend the boundaries of our biological heritage. As you drift towards sleep, consider for a moment the dark matter flowing through your room right now, passing effortlessly through walls, through your body, carrying with it the echo of the early universe. Think of the quantum vacuum beneath you, its virtual particles popping in and out of existence billions of times each second. Imagine the gravitational waves from distant cosmic catastrophes stretching and compressing the very space you occupy by a tiny, tiny fraction. The invisible universe isn't somewhere else. It's here, interpenetrating the visible world, undergirding everything we experience. We don't need to travel to distant galaxies to encounter it. We simply need to recognize that reality is richer, deeper, and more mysterious than what meets the eye. This recognition need not diminish us, but can instead inspire wonder. That human minds, themselves, collections of atoms organized by the same physical laws that govern the cosmos, can comprehend even a fraction of this invisible realm is remarkable. We are the universe becoming aware of itself, the cosmos reflecting on its own nature through the brief flicker of consciousness that we represent. As you close your eyes, know that darkness is not empty but full of possibility, full of unseen structure, full of hidden connections. The night sky between the stars is not a void, but a plenum, rich with dark matter, dark energy, gravitational fields, and quantum potentiality. Sleep is its own kind of darkness, its own journey into the invisible realms within. As your conscious mind surrenders to dreams, perhaps it mirrors the universe's own dance between the visible and invisible, between what can be directly perceived and what can only be inferred or imagined. Rest now, knowing that you are cradled in a universe far grander, far more intricate, far more mysterious than we can fully comprehend. Let the rhythm of your breathing align with the subtle pulse of cosmic expansion. Let your thoughts dissolve into the quantum probabilities of neural activity. Let your consciousness merge for a time with the greater mystery of existence. In the deep silence of the night, in the spaces between thoughts, in the darkness behind closed eyes, perhaps we come closest to experiencing the invisible universe directly, not through instruments or equations, but through the quiet recognition of being part of something immeasurably vast and fundamentally unknowable. Sleep well, cosmic traveler. Though the journey ends for tonight, the invisible universe remains, patient, persistent, and full of wonders still waiting to be discovered. The invisible universe is not empty. It is full of possibility, full of secrets waiting to unfold in the quiet spaces between stars. And though we may never see it all, we can feel its presence, subtle, persistent, and eternal. Sleep now, under its watchful veil, and drift through the dark, where the cosmos dreams.